Hello everyone. In this session, I'm going to talk about volatility, wherein we will get started with a few key definitions, where we will define what is volatility. We would also try to contrast it with a few other important related definitions like variance rate, etc. So that's one thing we will look at. Then bringing in another concept called power law. We'll talk about it, how we can use the power law in the context of the data that we are taking up to compute the volatility. In fact, this whole session, apart from making you understand the conceptual aspects of volatility modeling, I would also add up a couple of models which we are discussing conceptually here. The exponential weighted moving average model, as well as generalized autoregressive conditional heteroscedasticity model, or the GARCH model. We would try to work them out on a data set. For this purpose, I have taken one data set which is the closing values of Sensex, which is the Indian Bombay Stock Exchange, index values for the broad market based index Sensex. I've taken the data over the last 2 years, the values, and now based on that I want to use our model to estimate the volatility of the same, to understand how the volatility has been changing in the Indian stock markets, right? So we will be working parallelly in the spreadsheet apart from understanding the conceptual aspects. So in this context, I'll talk about how do you monitor the daily volatility, what are the weighting schemes that we have. These are conceptual aspects, but these two, we will look at them even practically on the data set. So I would look at volatility computation using the GARCH 1-1 model. We will see if there is any mean reversion present with respect to Sensex, and how do we really examine that mean reversion based on a GARCH 1-1 model. Once we have created or developed a model, I want to use that model to forecast the volatility, and even whatever the forecast that came out, how do I really assess the performance of that forecast. I want to look at that aspect as well, and using the GARCH 1-1 to forecast the future volatility. Finally, we'll spend some time in terms of understanding what do we mean by volatility's term structure. Just like a term structure of interest rate, we talk about the volatility term structure, where any definition of the term structure should be with respect to different maturities or different time period, what are the volatilities. So we will try to understand that aspect as well. So these are the various topics that we will take up in this session. Getting started, the basic definition of volatility is the standard deviation of the returns provided by the variable per unit of time, and that is when the return is expressed using continuous compounding. So when I have to express a return using continuous compounding, I have to find it like this. It's not SI final minus initial divided by initial. This is discrete compounding. So when I am looking at discrete compounding way of finding out the returns, I'll use this formula. When I want to find out the returns based on continuous compounding, I'll use this formula. So the price on the ith day divided by the price on the I minus 1th day, and taking the logarithm of that. That would be the discrete daily return. So what is the definition? Standard deviation of the return uh, for any variable per unit of time. So if I am collecting a daily data, the standard deviation will come out as daily standard deviation. If I have taken a weekly data, it comes out as weekly standard deviation. But in all these cases, the return needs to be expressed using the continuous compounding. So let me take my data. Okay, here we have over the last 2 years from 10th December 14 to 9th December 2016. This is the 2-year data we have and the Sensex values during this period. I'm interested in looking at the returns, right? Returns need to be, the daily returns need to be expressed using continuous compounding. So the continuous compounding, from here I can use log Si divided by Si minus 1. This is the returns computed based on continuous compounding. So this is how I got my returns. I will find the standard deviation of the return. So I can very well find the standard deviation of the returns provided by this. So I am taking the standard deviation of the returns, and this is what I call as the daily volatility. So I'll call this as the daily volatility of Sensex. Based on the data that I have, this is the daily volatility of the Sensex. I can very well express this in percentage terms, which says that the number is 0.99%. 0.99% is the daily volatility of Sensex. So for risk management purposes, standard deviation of the continuously compounded daily return is what we are taking. That is what I have explained you now. And standard deviation of the proportional change in the variable during a day. That is what we are typically looking at. Suppose the asset price is $60, daily volatility is 2%, and change in asset price is normally distributed. I want to compute the 95% confidence interval for the asset price next day. So daily volatility is 2%. So 2% of 60, which is $1.2, right? So this is the daily volatility in dollar terms. And now it is normally distributed. So 95% confidence interval for me is nothing but the mean value plus or minus 1.96 times the standard deviation. Now this volatility, which we have already computed, 2% of 60, which is 1.2. So this works out to be 60 plus or minus 1.96 times 1.2. So this is what will give me a 95% confidence interval for the asset price of the next day. So I can very well find out 60 minus 1.96 times 1.2, which approximately comes out to 57.6, and again the other side comes out to 62.4. So that's the kind of a range I am talking of, 95% interval. So if we, another important point regarding the volatility, if we assume that the returns each day are independent, right? Now every day, if I say this return is independent of this return is independent of this return. If I make an assumption that on all the days the returns are independent and with the same variance, right? The variance is more or less similar, they are independent. So what we are talking of is the variance of return over T days. Now instead of a daily return, now I am talking about a T day return. What is simply said is T times the variance of the returns over one day. So if I find out the variance of the returns over one day, right, I did not find the variance here. We have found the return. What we are saying is, if we assume that the returns of each day are independent and they have the equal amount of variance, then the variance of the return over t days is same as t times the variance of the return over 1 day. So it's as good as, now if I had computed the variance of 1 day, if I have to compute the daily variance, which I can find out either the square of the standard deviation itself, I can do that. So this is the daily variance. Now what we are saying is, if we assume this is for 1 day, the returns each day are independent and the variance is more or less the same, then if I want a 10-day return, 10-day volatility or 10-day variance or 1-year variance, all I am taking is take the daily variance and multiply it with t. So which means standard deviation has to be multiplied with square root of t. So here it's as good as saying 10-day variance, right, is as good as 1-day variance multiplied by 10. And 10-day standard deviation is nothing but the square root of 10-day variance, which is as good as saying, the other way of computing the 10-day standard deviation is you take the 1-day standard deviation and multiply it with square root of 10. So both of them should give me the same result. So which means if I have 1-day variance and I want to find out t-day variance, multiply it by t. If I have to have 1-day standard deviation and I have to get t-day standard deviation, multiply it with square root of t. Right? But the condition for this is the returns on every day should be independent, no dependency on the returns, and they should have the same variance. So only in that case this formula can quite comfortably be used. So it is quite easy to conclude that the uncertainty is increasing with the square root of time. The standard deviation is increasing with the square root of time. So you can very well find out what is the 95% confidence interval of the asset price after 5 days. So now that I know what is the standard deviation for 1 day, you multiply it with square root of 5 to make it the standard deviation for 5 days, and then do a plus or minus 1.96 times the value to get the 95% confidence interval for over a 5-day period. Now that is what is the volatility. But in the same context of volatility, we also have another important definition, which is the variance rate, which is nothing but the square of volatility, or typically the daily variance, which I have called. That is also called as the variance rate, which is the square of volatility. So here we already have discussed variance rate per day is the variance of return in 1 day. And if I want it for t days, you simply multiply it by t, which means the variance rate is increasing linearly with time. Whereas the standard deviation increases with the square root of time. Few more important points that you need to be comfortable with is the distinguishing between the business days and the calendar days. It has been observed that the volatility is much higher on the business days compared to holidays. So approximately so once we have computed daily volatility, if I have to compute annual volatility, I would consider that there are only 252 days in a year, which is what is corresponding to number of business days ignoring the holidays. So this is where if I want the annual standard deviation, I'll take a daily standard deviation and multiply it with square root of 252. So for Sensex, if I want annual standard deviation, I will take the daily standard deviation and multiply it with square root of 252, or precisely the number of trading days in a year. Probably in case of Indian markets, you may not find 252. It may be a 246 or 247 in general, but just to generalize the concept with the reality, we are talking about conceptually. I am finding out the number of trading days. I can very well assume it to 252, and based on that, I will find out the annual standard deviation, which works out to 15.67%. So the Sensex is typically operating at 15.67% annual standard deviation. Here we have another important definition of volatility that we need to be comfortable with, which is the implied volatility. It is, if for this you need to understand the Black-Scholes model of option pricing, which typically takes five important parameters: the current stock price, the strike price of the option. I'm not explaining the concept of option and all those here, but to find out the typical value of the option, it considers the stock price, the strike price, the risk-free rate of return, the time to maturity, and the volatility of the underlying. What we see is these four are readily available and they can directly be obtained from the market. This is the only term that I cannot observe directly. So this has to be computed. Now the definition of implied volatility is, instead of computing the market, instead of computing the value of the option, if I use market value of the option, means the price at which currently the option is trading in the market, if I take the market price of this option and then use this formula for reverse calculation, and based on that I obtain the value of sigma. So that particular value of sigma, where the market price of the option will be same as this particular formula's value. So that particular sigma is what we are calling as the implied volatility. And we see that if to understand implied volatility much better, we can very well look at VIX, which is the variability index or volatility index, which is the implied volatility of 30-day options on S&P 500 calculated from wide range of calls and puts. A kind of index is created which will give us a clear-cut understanding on whether the volatility is increasing or is it decreasing. So here when we are talking about a VIX based contract, a futures or option contract on the VIX, I'm not betting on the price at all. I'm only making a bets on the volatility of the option. So the volatility again forms an important aspect, whether it is, I have to differentiate between historical volatility and implied volatility. Implied volatility comes from the option related pricing, whereas the historical volatility comes from the data which we have computed. This is what is the historical volatility of the Sensex, which came out to around 15.67% as of the moment. Now, the next topic, see, in general, for a lot of computations involved with the 95% confidence intervals, with the predictions, we assume so many places that their data, especially the returns, is following a normal distribution. Let me just check in this case if it is following a normal distribution or not. Quick check is, I will look at the skewness of the returns. If the skewness is very close to 0, then I can say that the data is following a normal distribution. But here it looks somewhat negative, minus 0.62. And the same could be the case with kurtosis, even if it is close to 0. This is where I can think of a normally distributed data, but here I could see a big positive value 3.14, indicating there is a heavy amount of positive kurtosis, and this could be a leptokurtic kind of a distribution, right? So it's nowhere closer to normal, but in many of the cases, for many of the computations, we make assumption that the data is following a normal distribution. Whereas here, when I am talking about a power law, I can very well take it as an alternative to assuming normal distribution. So for majority of the variables that we are encountering in practice, it is appropriately true that the value of the variable has a property that when x is very large, the probability of b greater than x is kx to the power of minus alpha. And the same logic, if I am taking a logarithm on both the sides, the logarithm of the probability of b greater than x is same as log k minus alpha log x. So this is one important thing that comes out based on the calculations of the power law. One way I can look at is I can take some value of x, right? Probability of, in this case, if I want to apply the power law, I will take probability of b greater than, let me take 1%, 0.01 is something I'll take, and 2%. I'll take two numbers, right? And because I have two variables, I have to determine that. So what is the probability that the number is greater than 1%? So I'll take count if this number greater than 1%. If I look at it, it's around 64 observations are greater than 1%. Right, I have to divide it by the total number of observations, which is approximately 494 out of this data. So percentage wise, I am dividing it by 494 to get around 12.95%. Right, so that is the probability of x or v greater than 1%, 0.01 is coming out to 12.96%. Now similarly, so which means k x to the power of k, in place of x I am putting 0.01 to the power of minus alpha is equal to 0.1296. This is one expression that I am having. Then similarly I am taking the probability of, right, probability of this value greater than 2% is this much, which is working out to 1.01%. So I'll talk about k times 0.02 to the power of minus alpha works out to 0.0101, right? Based on this, I can find out my k and alpha. I'm dividing one by the other, resulting in k going off, 0.01 by 0.02, which is 1 by 2. So 0.5 to the power of minus alpha is this much, 1296 divided by 101, giving me the ratio wise, if I am dividing these two, it's working out to approximately 1 to 12.8. So 0.5 to the power of minus alpha is equal to 12.8. So minus alpha becomes log 12.8 by log zero point 0.5. So let me take that, right? So if I look at log 12.8, or let me look at log 12.8 divided by log the ratio between these two, which is 0.5. So log 12.8 by this will be my minus alpha, and if I am taking the negative of the same, it becomes my alpha. So from here I am able to find out for this power law alpha is 3.67, and based on that I can now find out what is the value of K, right? K into 0.01 to the power of minus alpha is coming out to be this much. So I can first of all look at K as 0.1296 divided by 0.01 to the power of minus alpha. So which works out as 0.1296 divided by 0.01 to the power of minus alpha. So giving me this is the value of K. Now based on this I should be able to find out the probability of V greater than X. So based on this, if I want to say probability of V greater than, right, probability of V greater than 3%, if I want to give, it's as good as Kx to the power of minus alpha, which is nothing but K into X is 0.03 to the power minus alpha. So that's how I use the power law. So it says that yes, if I want to talk about the probability of something greater than, based on this data, if I want to look at the probability of the return greater than greater than 3%, the probability of a return greater than 3% is hardly 0.23%. And if I want to look at the probability of V greater than minus 3%, so if I want less than minus 3, then I should take it as greater than minus 3 and then decrease the same. So here also I could simply see minus 0.03, which will not be applicable. So here I am more looking at the positive values of V itself, right? I'm not looking at the negative values in this process. So that's one more thing that we need to understand. Only the positive values for the variable is what we are looking at using this power law. So I can very well find out what is the probability of V greater than something. Well, the returns wise, if I want to use the power law, this is the way I can use. I can look at exclusively for the positive returns and I can make the decision accordingly. Then, how do I measure the daily volatility? We have already talked about sigma n is the volatility per day on the day n. On the nth day, if I really want volatility, the daily volatility, I'll represent it by sigma n. But this would be the value that is estimated at the end of day n minus 1. This is one important thing. So the volatility of day n is computed and estimated at the end of the day n minus 1. And we know variance rate is nothing but the square of volatility. So if I am taking the square here, it becomes the variance rate. If I am just taking sigma n, and it is the volatility. Continuously compounded return, something which we have already looked at. Now the way to compute this sigma n is the standard deviation, right? So this is how we compute the standard deviation in the normal form or the variance. Sigma n squared is nothing but each observation minus the mean whole squared divided by m minus 1, especially for the sample. Now here we talk about especially for our modeling of the daily volatility, a few things that we are making changes to this formula. This mean, whatever is there, I am assuming it to be 0, which means it becomes sigma n squared equal to 1 by m minus 1 sigma u n minus I squared. That's it. Because the mean we are assuming it to be 0 for the risk management purpose. And m minus 1 also I am replacing it with the mean. So basically all we are doing is the weighted average of the variance is nothing but the last m periods weighted average of the return square. The average, simple average of the return squared over the last m period is what I am taking as a variance rate for the period n. So, which means we are not relying on unbiased estimate. By making this m minus 1 replaced by m, we are moving away from using an unbiased estimate of volatility to a maximum likelihood estimate of volatility, wherein I can very well use m instead of m minus 1. So basically the assumption that is coming out is the mean daily return is approximately 0. And it's not something bad to assume as well. So probably if I look at the mean return daily, right, if it is a mean daily return, it looks like it's hardly 0.01%, which means it's very close to 0. And it is very small compared to that of a standard deviation. And even if it is not the case, I could very well create an adjusted return, which is where I subtract this minute value from all the days return. So the variance anyhow will not be impacted by change in the return value. So based on that, if you look at the mean now, after the adjustment, it should be more or less equal to 0. I could directly take it as 0, but if I have some kind of non-zero term lying, probably I can do this kind of a modification as well. So for monitoring the daily volatility, if you look at it, even on this, if I compute the daily volatility right through this process, I don't see any change here. Right, even if you look at 0.99 itself. So this and this are more or less the same, whether you are doing it on the returns or on the adjusted return, because simply adding or subtracting a constant will not change the volatility at all. So going with that, this is one modification that we are doing as of now. Then getting into the weighting schemes, if you see here, we just spoke about saying 1 by m times mu u n minus I squared across all the m values. So you could see that the return squared, we are adding last m periods return squared and dividing it by the m, which means every day's return squared, I am dividing it by the same number. So I am giving equal weight to each of the m days here. But in real world, because volatility is something not constant throughout, so based on how the returns are coming in the recent periods, the volatility should get impacted. So as per me, it looks like I should give more weightage to the recent data rather than giving a same 1 by m kind of a weightage to all the return squared values. I want to give more weightage to the recent return squared values and slightly lesser weightage to the older one. So instead of multiplying everything by 1 by m, I am coming out with a slightly newer formula, alpha I times un minus I squared. So alpha I is a weightage. So basically it's like alpha I, sigma alpha I should be equal to 1. The sum of all the weights will come equal to 1. But the recent ones will have a more value and the older ones will have a lesser value. So alpha I is the kind of weight that we are giving to observations I days ago. So if the I is 1 or 2, then alpha I should be much higher. But if the I is 100 or something, then the value of alpha I should be lesser. All the weight should be positive, no negative weight. But at the same time, when I am adding all these alpha i's, that should sum up to 1. Now, these is one set of models, right, where we are giving different weights to each of them, to each of the last m days, and multiplying those weights with the squared returns. So this model assumes that there is no long run average variance at all. All the variance is dependent on the last m days squared returns only. So there is nothing called long term average variance. Only the last m days will determine what is the variance of this particular security. So there is nothing called a very long run average kind of stuff. Whereas I can very well bring in even those kind of models wherein apart from this term, I'll also bring in one more term which is the variance rate long term VL, long term variance rate, which I am multiplying it with gamma, which means out of the total weightage I am giving some gamma weightage to the long run total variance rate, and the remaining 1 minus gamma weightage is going towards each of the last m days, right? So that way this total weights now become equal to 1. So these are the models where the long run weights are taken into consideration. These are the models where the long run weights are not taken into consideration. If I am building a model like this, I am not looking at long run average impacting the overall variance. Whereas if I am considering these kind of models, I strongly feel that long run variance rate is also impacting the variance of a particular set of data. And this is what gives rise to ARCH model. ARCH is nothing but auto-regressive conditional heteroscedastic model. So it is based on an estimate that variance is based on 1, a long run average, and 2, m observations from the previous periods. So that's how the ARCH m models have come out. The older is the observation, I am giving less amount of weightage to it, and the newer observations are typically carrying more weight. So if I simply take this product gamma into VL, gamma times the variance rate for long term, if I am taking this product as simple omega, I will write this as sigma n squared equal to omega plus this entire term, alpha I times mu n minus I squared summed up. So that's what we define ARCH M model. So which means I am considering the last M periods to estimate the volatility of the current period. So this is what we need to understand regarding different kinds of weights we can give to the squared returns of the observations, so that we can use them for the volatility estimation purposes. Now here comes two of the most important models that we want to look at. One being the exponentially weighted moving average model, where we will not consider the VL here. So there is no gamma component in this model, only the alphas. but the alphas also, they keep decreasing exponentially. So which means alpha I plus 1 is same as lambda times alpha I. So that's how it keeps going down. So alpha I will be lambda times alpha I minus 1. So that's how the weightages keep going down with time. So based on this, now if you are looking at, you can very well write it something like this. For sigma n squared, let's write this. Sigma n squared is what, if I am looking at sigma n squared, it is nothing but I am giving different weights, right? Alpha I u n minus I squared. So if I start writing it, this is nothing but alpha I time, we'll write expanded. Alpha 1 times u n minus 1 squared plus alpha 2 times u n minus 2 squared plus and so on. Alpha n times u n minus u0 squared. So now if I start looking at it, if I just take this term out, right? So now instead of alpha, let me call it as or let me keep the alpha as it is. So now I am saying alpha 1 times u n minus 1 squared. But if you look at this summation entirely, which is 1 day later sigma n minus 1. So there is a sigma n minus 1 squared that is coming up, right? So there is an alpha 1 to this, which is mu n minus 1 squared, and there is some other weightage that is going on to the sigma n minus 1 squared. So let me take some x times sigma n minus 1 squared. Again the same thing I can expand. Sigma n minus 1 squared comes out to me as again starting off from n minus 2 squared. So this is a kind of a recursive process. So I can very well write this as lambda times sigma n minus 1 squared plus 1 minus lambda times mu n minus 1 squared. So I could very well find out u n minus 1 squared as well as sigma n minus 1 squared. So here let me take return squared, which is u n minus 1 squared. So this one I am taking the squared, which is giving me the return squared for each of the days. Now we are saying, so I got the u n minus 1 squared, but sigma n minus 1 squared is something I still need to get. Right, and based on that I will be finding out the sigma n squared. So right now let's hold on to it at this point. But if you see overall, this is what is the cyclical process. Sigma n squared again gets expanded like this. So we will go until the last, and finally my alpha I will become 1 minus alpha times 1 minus lambda times lambda I minus 1. So the weights will keep declining at the rate lambda. So lambda times the previous weight will become the weight associated with the current period. So numerical wise here let's look at it, and data wise I'll go back. How do we do that? Suppose that lambda is 0.9. Volatility estimated for the market variable for day n minus 1. Sigma n minus 1 is 1%. And during n minus 1, the market variable increased by 2%. U n minus 1 is 2%. Find the volatility. Now we have already said lambda is 0.9. So now I can very well write this as 0.9 times sigma n minus 1 squared, which is 0.01 squared, plus 1 minus lambda, which is 0.1 times u n minus 1 squared, which is 0.02 squared. So based on this I can very well find out 0.9 times 0.0001 plus 0.1 times 0.0004, giving me the overall estimate of the variance and based on that take the square root, gives me the standard deviation of the process. So that's how we understand the exponentially weighted moving average model, but we still did not complete the model out here, right? So here I would like to go with sigma squared. I'll come back to it. How do we take this? Now we will move on to a few more important aspects out here. The data storage requirements are modest. Remember, at any given time, only the current estimate of the variance rate and the most recent observation on the value of the market variable, only those two are required. If you see here, overall I require only this, which means the variance as of the previous day and the squared returns as of the previous day. I don't need the whole long data that is before this. This is what we call as a Markov process, wherein I require only the data of the previous days to make estimates for the current day. Only one period data is sufficient for me to make the estimate. So here I require the variance of the previous day, I require the squared returns of the previous day, and that is what is going to give me the variance of the current. So this is what I am saying here. I require only the current estimate of the variance rate, which is sigma n minus 1 squared, and I also need the most recent observation on the value of the market variable, which is u n minus 1 squared. All the other old estimates of the variance rates, I can directly discard them, and even the older values associated with the market variable also will not be of any help to me. And this is the model which is very much used to used to track the changes in the volatility and even helpful for prediction of the volatility. And the value of lambda, right? In this case, in our earlier example, we have taken it as 0.9. Whereas the value of the lambda is very, very important. It is what really tells that to what extent the estimate of the daily volatility, whatever is the daily volatility that we are predicting, is reflected by the daily change in the variable. To what extent the daily change in the Sensex values is impacting the daily volatility as well. So if the lambda is very small, you see here, if the lambda is very small, 1 minus lambda will be very high. The high value of 1 minus lambda means un minus 1 squared is multiplied with a very high value, which indicates that majority of the weightage is going to the current volatility rather than that short term volatility that we got as of the previous day. So if the value of lambda is very small, then we are giving more and more weight to the recent, only the last observation. All other observations are carrying a lesser weightage. So whatever the estimate that we are producing for the volatility, every day will be very, very volatile because they are very much dependent on what is the underlying market variable on that particular day. What is the change that has occurred to the underlying market variable on that day? More commonly, though, we need a mechanism to find out the lambda. We'll use a mechanism to find out the lambda. But very commonly in the industry, we use 0.94 as the lambda value, but we can very well check it out as well. So if I have to go with the practical way of doing the same, what we do is for the earliermost observation, I will consider the sigma n minus 1 squared to be the same as un minus 1 squared. That's only for the oldest observation. That is where I start off. I consider that to be the oldest observation, and based on that I am assigning it the sigma n minus 1 squared at that point to be the same as u n minus 1 squared. But from the second period onwards, I'll take a value for lambda. Let's say I'll take it as 90%. We can very well change it. I'm taking a value of lambda, which means now I am taking from the second day onwards, I am taking it as lambda times sigma n minus 1 squared plus 1 minus lambda times u n minus 1 squared. That is how I am getting the sigma. So I am getting the sigma squared for all the days, and this is how I've got the sigma squared for all the days. This is the first step which we do as a part of the practical implementation part. Now I go with the process. Let me see if I have documented it. Otherwise, I'll again come back and go ahead with it. Now, okay, before I do that practically there, let's also understand one more model on the same line, which is the generalized autoregressive conditional heteroscedasticity model, or in short called as GARCH, generalized autoregressive conditional heteroscedasticity model, otherwise called as a GARCH model. The P and Q are associated with the previous P periods of un minus 1 squared and previous Q periods of sigma n minus 1 squared. In our earlier model EWMA, we have considered one period of un minus 1 and one period of sigma squared n minus 1. So the P and Q are more general. I consider up to n minus p and even sigma n minus p squared, right from n minus 1, n minus 2, n minus p. And similarly for Q, sigma n minus 1, n minus 2, n minus q. So the GARCH model, if I am just taking n minus 1 for u and n minus 1 for sigma, it becomes GARCH 1-1 model. So I have taken one period of squared returns and one period of the variance rate. So the sigma n squared is actually captured with some kind of weightage going to long-term volatility and alpha weightage going to the squared returns of the previous period and beta weightage going to the variance of the previous period. And the weights are given in such a way that the sum of their weights is equal to 1. So EWMA is a special case of GARCH, especially when gamma does not exist, right? Gamma is 0. And I could clearly see if the beta is lambda, so alpha will become 1 minus lambda. When this is the case, the GARCH is actually getting reduced to a EWMA kind of a model. So in GARCH 1-1, the way we are simply defining the things is the variance rate estimate that we are getting is based on the most recent, one last recent observation of the squared returns and one most recent estimate of the variance. So that is what is the GARCH 1-1 model being talked about. So now I need to have some kind of estimates of all these. So gamma VL, I am calling it as omega. I have alpha as a variable and beta as a parameter. So I have to estimate all these three. Once I know this, I know that alpha plus beta plus gamma equal to 1. So once I know alpha and beta, 1 minus alpha minus beta will become my gamma. And once I know the gamma, I know omega is nothing but gamma times VL. So based on this, I'll get my VL as omega by lambda. So that is how we find out the long-term variance. And a few important things that we have to keep in mind: if the GARCH model has to be stable, I require the alpha plus beta should be less than 1. The moment the alpha plus beta goes greater than 1, which is very much possible, In that case, I call that kind of a model to be a very unstable model of volatility. So instead of relying on GARCH model, I'll go back to work with the EWMA itself. And just like the way we looked at in case of EWMA, where the lambda keeps going down and down as the time passes, even here also, we see that the weights for the olden days, for the older days, typically go down and down at the rate of beta, which is otherwise called the decay rate. So now with all this information, we should be in a position to really execute the model on our data, and based on that use the predictions for volatility using the EWMA as well as the GARCH approaches. Now comes the next important aspect in terms of the computation. Now we have defined the EWMA model as well as the GARCH model. Whereas I have a few parameters to be estimated. In EWMA, I have lambda to be estimated, and in case of GARCH, I have alpha, beta, omega to be estimated, and based on this omega, I will get my gamma as well as the long-term volatility. All these things are there. So I need to have some kind of estimates of these parameters. So normally we are estimating the same from the historical data. So this is what is our historical data. So from here only I have to go ahead in terms of estimating the parameters. Now I will get a maximum likelihood estimate. I'll go with a maximum likelihood estimate, wherein I am making an assumption that all these returns typically follow a normal distribution. So when I'm saying maximum likelihood estimate, we are choosing the value of the parameter that maximizes the chance of the data occurring, a particular distribution. So here we will take the chance of the distribution to be more of a normally distributed, the returns follow a normal distribution, and based on that I want to choose the value of the parameters that maximize the chance that the data follows a normal distribution. So we are assuming a probability distribution of UI. So in this case we will assume that the UI will follow a normal distribution conditional on the variance, right? So that's the kind of distribution we are taking. So based on that, the best parameters are the ones that maximize the normal distribution density function itself. We know that the density function of the normal distribution 1 by root 2 pi sigma squared x minus mu by sigma squared. Now if you look at it, if you look at this thing, this sigma squared, fair enough, we have already got the values of the sigma squared. X minus mu we have taken it as 0, right? 1 by root 2 by sigma e to the power of minus half x minus mu by sigma whole square. That's the density function associated with the normal distribution. So the mean we have already got it as 0, so I am eliminating it. So the whole equation, the density function is becoming 1 by root 2 pi sigma squared into e to the power of minus half x squared by sigma squared. So this is what is the kind of expression that we have got. So what I can very well do is I want to maximize this expression. So based on this, I can first, let me start off with the EWMA part, right? EWMA likelihood. I will find out the likelihood with respect to EWMA model, where I have to take it as 1 by square root of 2 pi sigma squared is this one into e to the power of minus 0.5 times x squared, which is the return squared, divided by sigma squared. So this is what is coming out as the likelihood value associated with the EWMA. 1 by square root of 2 pi sigma squared into e to the power of minus half x squared by sigma squared. So this is what is working out as the likelihood function associated with the EWMA model. Similarly, okay, based on a lambda value of zero point 0.9. Similarly, let me take a GARCH sigma squared. So that is EWMA base sigma squared. Now I am looking at a GARCH sigma squared, where the sigma squared for the first one will be the same as the return squared itself. Now I have to take the values of alpha, beta and omega. Omega, I'll take a very small value 0.00001, right, which is gamma times VL. VL itself could be a small number and we are having another percentage gamma multiplied by it. So I'm taking a very small value. Let's say initially let me go with alpha of 0.05 and beta of zero point 0.9, something like that, right? And based on this, I can also compute a few things where my gamma has to be 1 minus of alpha minus beta. That's one thing. Now once I have got my gamma, I'll get my VL. The omega is nothing but gamma times VL. So based on that, VL is omega by gamma. So I have got my VL, and based on that I can form long-term volatility as the square root of VL, which is given by whatever. So now these three are unknowns for me, but now I have just assumed some numbers. So let me go with the GARCH sigma squared computation, where I am taking as omega plus alpha times, right, if you look at the formula, omega plus alpha times un minus 1 squared, which is this one, right, I am taking un minus 1 squared plus beta times sigma n minus 1 squared. So which is giving me this kind of numbers out here. Un minus 1 squared, sorry. Un minus 1 squared, right, here also did I do the same mistake in case of EWMA? Yeah, here it is fine, here also now it is fine. So I got the GARCH sigma squared, and based on that I can find out GARCH likelihood first, which again goes with the same fundamental, 1 by square root of 2 pi sigma squared multiplied by e to the power of minus 0.5 times x squared divided by sigma squared. So this is what is the GARCH based likelihood function that we have got. Right, so we computed the likelihood based on GARCH, we computed the likelihood based on EWMA as well. So now I want to maximize, right? So the product of these things need to be maximized, but this is going to be a very heavy number, right? So when I say the product of these things need to be maximized, 29 into 26, whatever is the product, that needs to be maximized as a part of maximum likelihood. So this is where we will generally use the log likelihood, because maximizing the product is same as maximizing the summation of their logarithm. So I will simply take the log of this so that I can maximize the summation rather than the product. So I have computed the log likelihood here, and even here I have to find out the log likelihood. So which is resulting in, I'm taking the logarithm values out here. So this is how I'm looking at the log likelihood function based on the GARCH, based on the EWMA. So means we are trying to find those values of the parameters in such a way that the overall return data is following a normal distribution. I want to get the maximum likelihood estimates of lambda in case of EWMA. I want to get the maximum likelihood estimates of alpha, beta and omega in case of GARCH, so that they maximize the chances of the data following a normal distribution. So now we are there. I can simply get the sum, right? The likelihood, the total likelihood value which I want to maximize. In case of EWMA, the total likelihood value is working out to some 1564.86, whereas in case of GARCH, again the total log likelihood value is working out to this much. So 1518. Now my objective is to maximize the likelihood and determine the value of this particular variable, of this particular parameter. Now this is where I can use the solver function of the Excel. So I would like to maximize this particular value by changing this particular value, and I have no constraints regarding the variables, right? So going with this, if I am looking at it came out that the lambda is 1.08 and the total log likelihood got maximized. Okay, this has to be between 1 itself, right? So this is where I'll again reuse the model. I'll set one constraint out here saying that this particular value should be less than or equal to 1, and this particular value should be greater than or equal to 0, because I want the lambda is a weightage. It has to be between 0 and 1 itself. So now when I think it looks much better, the lambda has come out to 0.9874. So lambda is much higher here. The total log likelihood got maximized at this value. So almost only 1 and 1.24% is typically being given to the recent observation, right? Because 98.74 is typically given to the sigma n minus 1 squared, and only 1.25% approximately is given to un minus 1 squared. So the recent observation is not that heavily impacting the volatility. So it looks like the volatility of the model needs to be very stable. So that is what I could see based on the EWMA model. Now let me see how can the GARCH give me a kind of a solution. So I want to maximize this value this time, wherein I am interested in changing all these three values, and the kind of constraints I have, I will set these two values beta and omega. Sorry, the changing, I want to change all these three, but constraints wise, okay, the objective for me is I want to maximize this. The constraints are these three are changed. Now let me give the constraints. So these two values, alpha and beta, individually they are less than or equal to 1. Alpha and beta should be greater than or equal to 0. Now what about omega? Omega is gamma times VL. Now though VL is positive, gamma need not be positive. So my omega need not be positive. So I don't want to set any kind of restriction with respect to omega. Unless I am making an assumption that the GARCH model is a stable model, because alpha plus beta will come less than 1, then my GARCH model will be a stable model. So if I am directly making an assumption that the GARCH model is a stable model, then I can directly put a restriction on omega as well. Otherwise, I want to leave the omega as it is. So based on this, if I am looking at, these are the constraints with which I am working out. Now let me see which can maximize the value of the total likelihood in case of GARCH. Okay, so it is working out that there is a negative value for gamma. Gamma is carrying a negative value. Alpha and beta are carrying positive values out here. Gamma is carrying a negative value, which is clearly indicating that the process is not stable, right? And because of which gamma is carrying a negative value out here, which is based on which means I cannot look at the GARCH as a model for implementation or for the prediction of the volatility here in case of Sensex. I am relying more and more on the EWMA model itself. So that's how we have got the various parameters of GARCH as well as the EWMA models. So this has to be understood from the spreadsheet computation itself. Now, in some cases, probably let me do one small modification for you, right? Let me just set this as 0.5 and this as 0.94 so that, okay, what does, sorry, 0.05. Okay, so let me consider some value for the long-term volatility and VL. Now, what I really want to look at is, I want to build a model where I will set additional constraint here with respect to omega, right? I'll set additional constraint with respect to omega, wherein I will say omega value should be greater than or equal to 0. I'll just set one additional constraint, so which has slightly different values altogether. I see that the alpha is going to be a 0.05, the beta is going to 0.94. This is the value of omega, resulting in a gamma of this much. VL is this much and long-term volatility is this much. So this is one assumption that I am making. I have explicitly set the omega value to be positive, which need not be the case, because I just wanted to explain the concept of mean reversion. In practice, the variance rates tend to pull back to the long run average level. And GARCH 1.1 model incorporates the mean reversion because we are talking about some gamma times VL. Whereas we don't see any kind of mean reversion in as per the EWMA model. Now let me take, from this example, let me take the standard deviation based on an EWMA model and standard deviation based on the GARCH model. Let me simply compute those two, wherein I am talking about the square root of sigma squared here right? And I could also take the square root of the number coming from GARCH. And if I try to plot these two standard deviations, so this is how the numbers are working out, right? So the GARCH is looking slightly more volatile, and you could see some kind of a mean reversion behavior that is coming in case of GARCH. If some volatility has come up, it is coming back. If the volatility has gone down, again it is coming back. So there is some level of mean reversion that is observed in case of GARCH, but it is not mandatory in case of EWMA model. So especially we have already talked about when there is some kind of mean reversion, then it's better that I use my estimates based on GARCH compared to the EWMA model. But when the GARCH model becomes very unstable, especially when alpha plus beta is greater than 1, that is what we got in the initial scenario, in which case my gamma will become negative, and then there is no meaning for the long-term volatility, etc. So in that case, there is no point in considering the GARCH model for the prediction purposes. It's better to rely on the EWMA itself. And we already know when the omega is 0, GARCH and EWMA remain one and the same. So this is the way the mean reversion can be looked at. And the mean reverted value, if I really want, I can take it as, right, that particular, see, if you look at the conceptually, sigma n squared, we are taking as gamma times VL plus alpha times sigma n minus 1 un minus 1 squared plus beta times sigma n minus 1 squared. Now when I am talking about this entire thing, I'll take the alpha, so sigma n minus 1 squared itself, alpha plus beta time. So basically the long run mean reverting level will come out as VL divided by 1 minus alpha minus beta. That will come out as the long run mean reverting level. So I'm taking the VL and say 1 minus alpha minus beta, which is nothing but my gamma, which is again an indication of the mean reverting level itself. So this level will be my mean reverting level. So 1.27% is the typical mean reverting level as such. When I have to look at the performance of the GARCH models in volatility forecasting, so we have already made an assumption underlying the GARCH model that the volatility changes with time. We understand that during some periods the volatility is very high, whereas in some periods the volatility is very low. So now if I have to really examine the performance of the GARCH model, so first look at the autocorrelation structure of the squared return. Okay, let me look at the autocorrelation structure of the squared returns. Let me just take this aside. Let me look at the autocorrelation structure of the squared return, this one, right? So let me do it with, let me hide this part so that we can do the analysis better. Now I want to look at, let me hide even a few more columns out here. The EWMA log likelihood, right? These columns I want to hide for now. Yeah, now let's look at here. I am more interested in looking at the autocorrelation structure of the squared return. So let me take autocorrelation right? Or let me start. Autocorrelation. I'm giving lag 1, 2, 3, just trying to understand for a few lags. I want to find it with respect to the squared returns. I'm finding out the autocorrelation structure. Probably I should do it for many more. But quickly I'm looking at the autocorrelation for the squared returns. So because it is first lag, I will consider one lesser out here, and I will consider from here. Again one lesser at the top. So this is what will give me a 1 period lag autocorrelation. So I am taking the u squared from period 1 to period n minus 1 to period 2 to period n. That is giving me the lag 1. So approximately this is 0 itself. Right? The return squared is approximately 0 out here. Similarly, now if I have to consider the same for lag 2, lag 3 as well, all I'll make the changes here is I'll take 2 lesser out here, and again I'll start with 2 lesser out here. So here I see that the correlation is 0.06, and if I'm talking about for 3 periods, 3 period lag autocorrelation, it looks like it's around 0.04, and probably if I want to try a few more, okay, for 4 periods it is working out to 0.01 again, and for 5 periods it's working out to 0.02. So almost the autocorrelation squared is much, autocorrelation of the squared returns is much lesser. If the GARCH model is working well, it should remove the autocorrelations altogether. So if I look at the autocorrelation between the squared returns by the squared by the variance, right? So I'll call return squared divided by sigma squared. If the GARCH or the EWMA, let me look at it with the GARCH directly. So this number divided by the GARCH sigma squared, if I am taking this, now I consider the autocorrelation here. Between these terms, I consider the autocorrelation. So which means instead of E, I am going with N column. That's it. Right. If I am considering if the GARCH model has done a good job, the for this ratio, the autocorrelation needs to be reduced. But here I am seeing that it has typically gone up. Right. The same logic I can very well think of. Now if I am trying to drag this out here, instead of F, I just need to consider N. So let me see how the autocorrelation is working with the adjusted squared return. So minus 0.06 again. So I didn't see that any kind of a major improvement coming up. So that's the reason we didn't find the GARCH model to be much more appropriate to this particular data set. Now again here it is 0.05. So what we are simply saying is you can directly examine the autocorrelation of the squared returns. If the GARCH model or a EWMA model, I don't need to segregate both of them because both of them are the same piece, except for the omega is 0 in case of EWMA. Anything is working well, it should remove the autocorrelation altogether. So One way is first look at the autocorrelation structure of the squared return. It should appear that the autocorrelation is appearing in the squared returns to some extent. And once you do it for the adjusted squared returns, the autocorrelation should be completely eliminated from the model. So if the autocorrelation with squared returns divided by sigma squared, if it is much lesser, then I can very well say that the GARCH model or the EWMA model has done a good job in terms of improving the in terms of removing the autocorrelation structure, which means the volatility now is captured in a much better manner. Apart from that, we also have a junk box statistic, which is much more of a statistical scientific test. So I'm talking about a series having m observations. So here if I look at, I have 494 observations altogether. The junk box statistic is m times, which is 494 times. We are talking of sigma from k to equal to 1 to capital K, WK squared. Now CK is the autocorrelation for a lag K. Right now I have in this case autocorrelation for lag 1. Right, I am having the autocorrelation for lag 1, 2, 3, 4, 5. Let's say I am talking about for 5 lags. CK is the autocorrelation for lag K, and K is the number of lags considered. So I have considered 5 lags. So basically it becomes 494 multiplied by W1 C1 squared plus W2 C2 squared plus so on W5 C5 squared. So this I have to multiply it with M. Right? Now the weights which we are talking of will be 494 plus 2. The weights now that we have to see, we have already got. These are the 5 CKs. Now I am also considering the weights as 494 plus 2, 496 divided by M minus K, which is for the first one it becomes 493. So here the W's, the weights, will simply become 496 by 493. Here the first one will have a weight of 496 by 493. Then for the second one it becomes again m by 2. M is the number of observations. So m plus 2. Again it becomes 496 by 492. Right? Because I am taking out k. K is 2. So again here I can write it as 496 divided by 494 minus this. I can directly take this. So these are the weights that I am getting across. So these are the 5 weights. Right? So 496 divided by 494 minus this. So now I am multiplying 494 into, so first of all I have to multiply W1 into C1 squared. So I am taking this as W1 multiplied by C1 squared. So like that I have W2 multiplied by C2 squared, W5 multiplied by C5 squared. So this is one calculation that I am doing. Then I have to add all of them, multiply it with 494. So I am doing the summation of all of them and I am multiplying it with 494. So I have got just a number of 3.8. Now this I have to validate it with the table value associated with the junk box statistic, and based on that I will be making a conclusion whether the volatility model is a fitting model or it's not a fitting model. So we have to refer to the table values to make the conclusion. So you can do the same for the UI squared, or you can also look at UI squared by sigma I squared also to look at to check the effectiveness of the model. Now once your model is there in place, you can very well use it to forecast the volatility. So wherein you are directly taking the formula, just small derivation part, you could look at sigma n squared. I am taking it as gamma times VL alpha times u n minus 1 squared plus beta times sigma n minus 1 squared. So small workout that I am doing. So you could look at it here. Let me do it here. Sigma n squared is nothing but 1 minus alpha minus beta VL plus alpha u n minus 1 squared plus beta sigma n minus 1 squared. Now let me expand this. This is VL minus alpha VL minus beta VL plus alpha u n minus 1 squared plus beta sigma n minus 1 squared. Now let me take this VL to the other side. So this is what becomes sigma n squared minus VL. I am taking alpha out, u n minus 1 squared minus VL plus beta out, sigma n minus 1 squared minus VL. That is the step. Now I am talking about this as time period n. But if I am talking about a time period n plus t, I could directly take sigma n plus t squared minus VL alpha times u n plus t minus 1, just substituting n plus t in place of n. So this is the step that I am getting. Now when I want to look at the expected value of the un at any future date, I am talking about the expected value of this is same as the squared variance itself. So that is making me to substitute. When I want to take the expected value of this much, I am taking the expected value of this to be the same as this itself. So which is where I can combine the stuff, saying alpha plus beta times the expected value of this. So directly it is coming out. Now when I am trying to bring it to the nth period, if I keep repeatedly doing this stuff, it simply becomes alpha plus beta to the power t times expected value of sigma n squared minus Vn. So that's the reason if I want to find out the variance of t periods from now, all I am taking is the long term variance VL plus alpha plus beta to the power t times sigma n squared minus Vn. So this is the number that I am typically taking. So if I have to simply go ahead with each of the periods projections, right? Let's say for the future I want to make a projection. All I am doing is I will be considering VL from the next period. If I want to look at for the future the estimate of this, I have to consider the VL. For that I have to expand this, unhide this. Okay, so these are my numbers. So let me consider equal to VL, which is my long term variance, plus alpha plus beta to the power t. So here we will consider it as 1. Alpha plus beta to the power 1, this is for the first period, times sigma n squared minus VL. So sigma n squared is the previous period, whatever we know. Sigma n squared also I can take it as frozen because that's the only period that we know, minus VL also I can freeze it, which is this particular number, right? Now this will give me the estimate of the variance. So let me somewhere consider the periods as 1, 2, 3, at least for the next few periods. Let me consider this, and here instead of 1, let me focus this one. Now I could see this is how the variance is going to move over the future for the next few periods. Going with this model for the next few days, it's going to be 1.02, then it goes to 1.03, 4, 5, 6, and probably once it touches the 27, again it can come back to 1.12 or whatever, whichever was the long term one, it can very well reverse back. So in EWMA, expected future variance rate is equal to the current variance rate itself. So I don't have this kind of a estimation for longer periods in EWMA because alpha plus beta in that case goes equal to 1. So there I can directly consider the expected future variance is more or less equal to the current variance rate itself. Whereas in case of GARCH, especially when I get alpha plus beta as less than 1, we see some kind of mean reversion level of VL, and the reversion rate is going to be 1 minus alpha minus beta. But if it is greater than 1, there is no point in considering the GARCH model all such, because the kind of weightage that is going to the average long-term variance is negative. So it is not mean reverting anymore, it's more and more of mean fleeting. So there is no point in considering the GARCH model for the volatility estimation and forecasting purposes. And finally, one more topic that we need to understand here is the volatility term structure. Especially if I want to define the volatility of a T period as expected value of sigma n plus T squared. And I will define another variable called A, which I will define it as log 1 by alpha plus beta. Now going with our earlier statements, I can take it as expected value of sigma n plus T squared. I'll take it as VL plus alpha plus beta to the power T times sigma n squared minus VL. Now what we are, based on these things that we have taken, I'll take Vt, expected sigma n plus T squared, I'll write it as Vt. So VL alpha plus beta. Now if I say A equal to log 1 by alpha plus beta, right, e to the power of A is 1 by alpha plus beta, and alpha plus beta will be e to the power of minus A. So alpha plus beta to the power T will become e to the power of minus AT, and this will become sigma n is nothing but V0 minus Vn. So this is where we are calling this Vt is an estimate of the instantaneous variance rate in T days based on the current value. So the average variance rate per day between today and time T, if I want to look at it, I will have to integrate this over the entire T period. So I am integrating it over T and dividing it by T. And this value, if I am integrating it, going ahead with the integration, this is a constant, so I'll keep it as it is. And V0 minus VL is a constant, and e to the power of minus AT, I have to take the integration of that. So integration of e to the power of minus AT is nothing but this divided by minus A, and I have to substitute between T and 0, giving me a e to the power of minus AT minus 1. So 1 minus of e to the power of minus AT by AT is what we are getting. So this is the kind of an expression that I am getting for the instantaneous rate of volatility for each of the periods. So as T is increasing, this is approaching the long-term volatility, and I can very well compute the volatility of the various options and their maturities directly from this model, or I can also estimate from the GARCH model. So this is how I understand the volatility term structure. I can use this by substituting now the different values of t. I can very well model how the volatility is going to change for a different time period, which I can very well use for the various option related trading strategies as well. So this is what I wanted to cover as a part of this session on volatility. I hope you have got a complete understanding regarding the various models that we have discussed, various conceptual aspects that we have discussed regarding the volatility. If you have any further queries regarding the same, you can very well get in touch with me by giving me a call on the number that I have given below, or you can even send in an email at vamsidhar@pacegurus.com. Thanks a lot for listening to this session. Thank you very much.